when we talk about the barrier model and the Arrhenius equation, the barrier model is sort of like a theoretical concept of what's happening during the reaction, and then the Arrhenius equation is we're going to use that. It's going to talk about activation energy and how that relates to temperature, sort of the relationship between things and temperature. Okay, so we're going to talk about energy in this section, so let's go back and remind, when we see the symbol delta, the triangle, that always refers to a change of something, and it's always defined as the final value minus the initial value, so that if signs matter, we're always going to get the same sign, so we always do final minus initial. So when I see delta E, E is internal energy, and that means all of the types of energy of the reactants and products, the system. H is enthalpy. It's a specific type of energy, so it's a specific kind of energy that's part of the total internal energy, and also enthalpy is usually related to expressed with heat changes, so we often call it, sometimes instead of saying the enthalpy, they'll say the heat of. So the enthalpy of reaction or the heat of reaction. So if I put a delta in front of E and I use R standing for reaction, so delta ER means the energy of the products minus the energy of the reactants, the internal energy of the products minus the internal energy of the reactants. Or I could talk about enthalpy, which is just one kind of energy, but still gets me useful information. Delta HR means the enthalpy of a reaction, and it's the enthalpy of the products minus the enthalpy of the reactants. Okay, also, we're going to do energy diagrams. Remember, we usually put energy on the y-axis, and then I have different heights, and the difference between two heights of, this would be, since it's pointing this way, that means this is the final and this is the initial. So this would be representing the value delta E of the reaction, so the change in energy of the reaction. All right, so now let's talk about what we expect happening in a reaction. So we're going to use these things called reaction progress diagrams or reaction profiles sometimes. And these energies are sort of saying what is happening to the energy throughout the process of the reaction. In Gen Chem 1, you probably did some thermochemistry where you talked about specific heat and enthalpies of reaction. Now we're kind of looking more on the theoretical side of why is it changing. So we can imagine life begins, the reactants have some energy, some internal energy. So I might put there's different ways it'd be some kind of internal energy or Gibbs free energy or enthalpy or some kind of energy unit on this y-axis. And sometimes it just says energy. So I start with some reactant energies, which means before the reaction becomes that should be static, like they're not changing, they have some energy, it's a flat line. In order for the reaction to happen under this collision model, like the reactants are going to have to come together and they have to form something we call a transition state. And in this transition state, like it's kind of half between reactants and products. It's like partially broken and formed bonds, and it's always a very high energy. It's highly unstable. Otherwise it would exist all the time. So it's this high energy state that exists for a short period of time, but it's unstable, so then it's going to break apart and make products. So we always are going to have some kind of barrier, and this barrier, at the top of the barrier, that is the transition state, this intermediate complex that's sort of between reactants and products in the course of this reaction. And again, we're going to call it a barrier, and the top of that barrier is the transition state. And then after this transition state, now it's unstable, it breaks apart and it makes products. So we see the products will be lower in energy. I don't know if the products are going to be lower in energy than the reactants or higher in energy than the reactants, but they're definitely going to be lower in energy than the transition state. That transition state will be the peak, the barrier. So now I can refer to something called the activation energy. So the activation energy is the energy between the reactants and the transition energy, the transition state energy. So we'll see that in the next one. So that if we look at these activation area, so this barrier, this transition state is related to there's some amount of energy it takes to get to this high energy state that is the state that I need to access so that the reaction can proceed. And that activation energy will always be the difference between the reactant, it's the change from the reactant energy to the peak energy of the barrier, which is the transition state. So from the reactant energy all the way up to the transition state energy, this is my activation energy. And the symbol for it is E with a subscript of A, which is faster than writing activation energy. So, and then I also have something called the enthalpy of reaction, remember, but that's about the products and the reactants. It doesn't involve the transition state. So for the enthalpy or the change in enthalpy or the change in energy, we're looking at the energy of the products minus the energy of the reactants. And so we will see that this is in this case, we have the delta H. The products are lower in energy than the reactants, so it gives off energy. And so this would be a negative delta H, and it would be an exothermic reaction. So if the products are less than the reactants in energy, we'll end up with a negative delta H, because this number is lower than this number. When I subtract final minus initial, I get a negative number. So a negative enthalpy tells me they're lower in energy, and it's an exothermic reaction. If the product was higher, we'll see it on the next slide, higher in energy than the reactants, but it would always have to be lower than the barrier. So it would kind of go like up and then go here. Then I would end up with a positive enthalpy change, and that would be an endothermic process. Key fact, this is going to come up. The higher the barrier, the slower the rate of that reaction, because it is going to need more energy to get over, so it slows down. Like sometimes the reactants collide, but they don't have enough energy to get over the barrier, and so they just break back apart. So I have to get up to that transition state. So it's not going to happen on every collision, and therefore we're going to see that the higher the activation energy, the slower the rate of that reaction. Let's look at what these endothermic and exothermic look like. So on this one we have an endothermic. So we see that the products are higher in energy than the reactants. It's going to take some amount of energy to make the products. So my enthalpy, or my change in energy for the reaction, is from the reactants to the products. So this is my change in energy. If it was enthalpy on this axis, it would be delta H of reaction. And then for my activation energy, it's from the reactants to the transition state. So this is my activation energy. Note, here I have reactants going to products, but my products are now lower in energy than my reactants. So my enthalpy will be energy of the products, or in this case, change in energy will be the enthalpy of the products, energy of the products minus the energy of the reactants. This is going to be a negative value, so this is exothermic. Again, my transition state is from the reactants to the my activation energy. It's from the reactants to the transition state. So this is my activation energy. We're going to have tasks where you get these diagrams and you're going to have to interpret them. You might have to come up with, tell me what is the activation energy, or label the activation energy arrow on the diagram, or determine the enthalpy of the reaction. So, kind of make sure you're clear and know the difference between an endothermic and an exothermic reaction profile. All right, so let's talk about a few more things. We're going to be hitting this a lot in the next chapter when we talk about equilibrium. It turns out that reactions don't just happen in the forward direction, they also happen in the reverse direction. So my reactants can form products, but my products might be able to also form that same transition state and then go back on the other side and make reactants. So I can consider this same reaction from the forward direction, where we're going from left to right, but I can also think about it in the reverse reaction, where the products are the reactants and they're going to the reactants, which are really the products, in the reverse reaction. So in the reverse reaction, we're going from right to left. So in the forward direction, the activation energy is from the reactants to the transition state. So this would be the activation energy of the forward reaction. But I can also kind of calculate the activation energy of the reverse. And so in this case, it's the products, but in the reverse reaction, the products would be the reactants. I know that gets a little bit confusing. So I'm going from the products to the transition state would be the activation energy of the reverse reaction. And so I could calculate that. Turns out that the difference between the products and the transition state would be the activation energy. And we don't put forward, if you don't say forward, we assume it's forward. But if it's the reverse reaction, we always kind of have to indicate it's the reverse reaction somehow. One more trick. it turns out an alternative way to find the change in energy of the reaction is to compare the difference in activation energies. We'll see that if I want to know this value here, the enthalpy of the reaction, or in this case, since it's showing energy, the change in energy of the reactant, I take the activation energy of the forward direction minus the activation of the reverse energy, activation energy of the reverse reaction. And I end up with the energy of the reaction. And so this is an alternative way to do this. Sometimes that shows up on different questions. So I said probably would have been just as easy. But if you didn't, maybe you didn't know, you knew these activation energies, but you didn't know the actual enthalpies or energies of the reactant and products, you could find it this way. All right, so we also could have a multi-step reaction progress. In the next section, we're going to start talking about mechanisms and multi-step reactions. I can identify a multi-step reaction because each step is going to have its own transition state, which means I'm going to see a barrier. So the fact that this reaction profile has 2 barriers tells me this is a 2-step reaction. If it had 3 barriers, that would be a 3-step reaction. Each of these steps has its own activation energy. Note that now I have 1 and 2, because now I have to say, well, which activation energy am I talking about? And when we're doing an activation energy in a multi-step reaction, we're always going to go from the products, as in just before that step began. So for the first step, it's the true, I'm sorry, I said products, I meant reactants. The energy of the reactants to the height of the first transition state. That's going to be my first activation energy. But then it comes back down. We can see this little plateau that is barely at, it's just this little minimum, is the products of the first step. They're going to continue on in the second step to react further, but so this would be the reactants of the second step. So for the second activation energy, I'm going to go from the minimum between the barriers to the peak of the second hump. And this would be my activation energy for the second step. And then overall, my enthalpy of reaction would be still my products minus my final products minus my initial reactants. So, and this is also because we know the higher the activation energy, the slower the reaction. Note that because the first hump, which happens to be taller, but it has a higher energy activation transition state, but the activation energy of the first one is very big, and the activation of the second reaction is very small. So we would say that this first step would be the slow step, and here the second step would be a faster step, because remember the rate of the reaction, the higher the activation energy, the slower that rate step. So this will be something we can interpret from these reaction profiles. Now we're going to bring in some math, because the pictures are fine and we see what's going on. Now we're going to bring in math. And now the reason why I had to do that first was because we're going to talk about how the activation energy affects the rate of the reaction and how temperature changes the reaction, the rate of the reaction as well. So we already said that the higher the activation energy, the slower the rate. So the slower the rate would mean the lower the rate constant. And when I take e to the negative number, the bigger the negative number, e to a negative power will get me a smaller value. So you can just play with it on your calculator or just trust me. So this is the Arrhenius equation. The rate constant of a reaction is equal to we call this a frequency factor or pre-exponential factor, but it's like a constant for that or parameter for that reaction, times E. This is E, the constant E, which I think is like 2.7, but it's the E button on your calculator. 2.37 I think is or 2.73. Has some actual number like pi does, but I just put the E number on my calculator. So E raised to the power of, now I have a term that has the activation energy and has the temperature. So I have negative activation energy divided by R. This is the gas constant, and you use gas constant in Gen Chem 1, but you use the one that was liters, atmospheres per mole Kelvin. I'm going to use a different version. Same constant, but I'm using it in different units. we're going to use this one, 8.314 kilojoules per mole Kelvin. I will give you that R value. So that's on the bottom times the absolute temperature. Remember, when we do temperatures, absolute temperature has to be in Kelvin. So we measure it in the lab in Celsius, but when you do this formula, you have to use Kelvin. So notice if the temperature is bigger, then this overall number will be smaller. But e to the negative smaller number will get me a bigger K. So follow the math or trust me. As you increase the temperature, it's going to increase K. It's going to increase the rate of the reaction. And we'll talk a little bit more in the next session about why that's true. All right, but let's now see how I can use the Arrhenius equation. It's kind of complicated, right? We don't like exponents. So again, what's going on? If we think about the barrier model, it kind of makes sense that the rate is affected by this activation energy and the absolute temperature. So the higher the activation energy, the slower the rate. Makes sense because it's got to get that much energy to get up there. So what do we mean by get that much energy? So the activation energy is coming from the collision. In a collision, I'm going to have an exchange of energy and with the surroundings. Also, the energy is coming from the kinetic energy of the particles. So they have some kind of energy, but now at a certain temperature, I'm changing so that now I have kinetic energy on top of the enthalpy energy. So the activation energy is how much energy is needed to pass over the barrier. So at higher energies, it's harder to pass over the barrier. So it makes sense that the reaction is less likely to proceed and I'll have a slower rate or a lower rate constant. Absolute temperature, remember, refers to the kinetic energy. So if they're at very high temperatures, they have a lot of kinetic energy. When they collide, there's a lot of energy they have to get to that transition state. Therefore, at higher temperatures, they're more likely to have enough energy to get to that barrier to proceed. And that means the reaction is going to speed up, so I'm going to have a higher K value. All right, so what is A, this constant that comes in front? Kind of complicated. It's actually two parts to it. What I want you to know, theoretically, A is about the number of attempts per second that the reactants attempt to cross the barrier. So how many times does it collide? But also there's an orientation factor, like how many times does it collide, but also are they in the right orientation, and then do they have the right energy? So, but in practicality, it's like something we solve for by fitting the data and saying, which value of A works to match the data with this model. So we collect K and T, we fit the data to a curve to find the activation energy and to find this A, and it just becomes a number like a rate constant we just put in there. So don't worry too much about it, but you will see that referred to. All right, so how can I use this to use experimental data to find the activation energy? This activation energy is a big deal. Big deal in biochemistry, mechanisms, and understanding what's going on is like, wait, what is the activation energy? This is very useful in thinking about what's going on with reactants. So I want to find the activation energy. How can I find it from experimental data? Well, I know that the activation energy and the temperature are related to the rate constant. So I'm going to measure the rate to get the rate constant. I know the temperature of the reaction. I can use this data to get the activation energy. So when we're doing these, we're going to be involving kinetics data that's got the rate constant or rate and temperature. So I'm going to do a reaction, find the rate constant, and I'm going to do it multiple temperatures. So I have K and T data that I'm going to use. So in method one, if I have two variables, right? So I have K, I have T. I want A and EA. Well, in theory, two variables, two unknown parameters. Now, what's the difference between a constant, a parameter, and a variable? A variable is something that's always changing, right? Like time is changing, temperature is changing, the rate constant's changing is, of course, the reaction. Those are variables. A parameter is something that's constant, but only for a certain set of conditions. So, like for one reaction, I might have one rate constant K, or for another reaction, I might have another one. In this case, I might have different reactions have different activation energies and different pre-exponential factors. So for a reaction, A and EA are constant, but they're only for that reaction. I go to a new reaction and they're different. So that's what we mean by a parameter. It's something that's constant but only for a given set of conditions. Whereas a true constant like pi or E or the gas constant R is a fixed value that never changes. So when you hear that term parameter, that's what I'm referring to. But two variables, two unknown parameters means I need two equations. Each equation can only get me one unknown. So what I'm going to do, you don't have to do it, I did it for you. I'm going to take the log form of this, the ratio form of this, and then I'm going to take the log of it. So I'm going to write this out for K2 is equal to A e to the negative EA over R times T2. And then we do it in another condition, K1, T1. And then I take the ratio of them, and then I take the natural log of them, and then I do some rearranging, and I get this. So you're just going to take this. It comes from here, but this version. The natural log of K2, so the rate constant for trial 2 over the rate constant for trial 1, is equal to the activation energy divided by R times the inverse temperature of the first trial minus the inverse temperature of the second trial, and temperature in absolute Kelvin. Note that this one doesn't have a negative sign, this one does have a negative sign, but they're switched. Now this is T1, inverse of T2 versus T1. So this is the one that's normally used. This one makes more sense how it came from the original one. You're going to want to know this equation. This is one of the forms of the, you're going to have three forms of the Arrhenius equation. The original, the ratio form, and I'll show you another one on the next page. So if I have two data points of rate constant and absolute temperature, I'm going to use this form. So note that I know two rate constant, I have two temperatures, I can plug them in, and now I can rearrange this and solve for EA and R. Well, I solve for this ratio, I get this E over R, so then I will, once I have this, I multiply it by R, I get EA by itself. And then once I have EA, I'll go back to the original equation with one set of the values, and I solve for A. So that's method one. Method two is I can now, if I take many, many temperature points, many, many Ks. So now I don't have just two, I have like a whole bunch, which means if I have a whole bunch, I'm going to graph them. So I'm going to take the log form, the natural log form of this. So I'm just taking this and I'm taking the natural log form. It turns out I get the natural log of K is equal to the natural log of A minus EA over R times 1 over T. I did some log math, right? This is the log of a product. I can break it out into a sum of the logs, and then I have an exponent, so I can put that in front, blah, 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 blah. So this is the third form of the Arrhenius equation you want to know. So I measure this rate constant and temperature many times, and now I'm going to take for every temperature point that I have, I'm going to take the inverse temperature, and for every rate constant that I found, I'm going to take the natural log of it. And I'm going to make a plot of the natural log of K versus the inverse of the absolute temperature. So here's my X, inverse temperature. Here's my Y, ln K. So I have Y is equal to some constant, because A is a constant, so the log of A is a constant, minus EA over R, some constant, times X, or Y is equal to M X plus B. I'm just going to switch them. So this is a linearized format of this equation. However, what is linear about it is I have to use the natural log of the rate constant, and I have to use the inverse of the absolute temperature. And if I do that, then the slope of this line, I make this plot. So anytime you see a plot with log of K and inverse temperature, you know it's for this Arrhenius plot. Then the slope of that line is going to be equal to negative activation energy over R, which means if I rearrange it, the activation energy is now negative time of the gas constant, 8.314, times that slope. Also, this is going to be my B, my y-intercept. My y-intercept is equal to the log of A. I want A, not the log of A, so I have to do some log math, and I exponentiate to the power of E, both of these, and I get that the pre-exponential factor is equal to E raised to the y-intercept of that same graph. So I get EA, I get A from this reaction. So both methods work. and it's basically what data are you given to use which equation.